So let's take a look at this problem. Two rigid, well-insulated tanks are connected by a valve. So the tanks are sitting here. Call this tank A, call this tank B, and they're connected by a valve which is currently closed, but there's a handle on the valve and you can open the valve. And tank A, they give us a volume of the tank A. It's 0.3 meter cubed. And it's initially filled with nitrogen. And the temperature initial of the nitrogen is 40 degrees C. And the pressure initial of the nitrogen in tank A is 850 kilopascal. And of tank B now, we find that we're not given the volume of tank B, we don't know that, but we're given the mass of the oxygen that's in tank B initially, and it's 2 kilograms. And the temperature initial for the oxygen in tank B is 88 degrees C. And the pressure initial of the oxygen in tank B is 313 kilopascal. The valve is opened and the gases are allowed to mix. Now again, you have to look at these terms. They're rigid tanks. What does that mean about the volume of tank A versus the volume of tank B? They don't change. You just open the valve. One didn't sort of expand. The volume of tank B didn't expand or change, right? And they're also well insulated. What does that imply? There's no Q, no heat transfer with the surroundings. Now, when they mix, you have one gas is colder than the other. Which gas is colder initially? The nitrogen is colder than the oxygen. After they mix, are they going to still be cold oxygen and cold nitrogen mixed, or are they going to be lukewarm? It's going to be a lukewarm mixture. So there's going to be some heat transfer, but it's between the two gases. And so if you define your system as the combination of the two gases, so that's our system, does the volume of the total system change during the mixing process? And that's a big observation. And a lot of students will struggle, and that's one of the keys. It's like, oh, I have two rigid tanks. I'll take the volume of both tanks as my boundary of my system. And so I know that the volume A plus the volume B doesn't change. And now you know the temperature, you're looking for a final temperature. I guess you could redraw this illustration like this kind of quickly. Think about at the final state. At the final state, you're going to have a mixture of N2 and O2 on both sides. And there's not going to be any difference in the mole fractions between the left side tank and the right side tank. They're well mixed. They have the same composition, and they're at some final temperature, T2, and some final pressure, P2. Okay, so let's see what they're going to ask us to calculate. For part A, determine the molar analysis of the final mixture. So they want Y sub O2 final and Y sub N2 final. I could add a subscript on that 2 for final state after the mixing, but let's just leave it like that. And then the final mixture temperature in degrees C, T2. I could say T2 of the O2 is equal to T2 of the N2, but we just say T2, right? Final temperature. And then the final mixture pressure, P2. And the last, part D, what is the amount of entropy produced? What symbol do I want to use for that term that I'm going to calculate? Is it sigma? Is that the amount of entropy that's produced during this mixing process? Sometimes I'll put 1 to 2, indicating, just like Q, the amount of heat transfer from 1 to 2, is saying this is the amount of entropy produced during the process, starting from initial state 1 and ending at state 2. But the book doesn't do that, so we'll leave it off. We'll just call it sigma. Okay. Now, the units of temperature, I just blew through that. Degrees C makes sense. Units of pressure, kilopascal, makes sense. Units of entropy produced. kilojoule per Kelvin? Is that correct or a typo? Is it okay? Yeah, it's okay, right? Now, sometimes those questions aren't so trivial and you got to struggle with it because sometimes, unfortunately, there is a typo in your textbook, on your exam, homework, or whatever. So, or my lectures, right? So you have to fix it or help me fix it. All right. They also say right here at the bottom, for the nitrogen, use constant specific heats with these values of C sub P and C sub V, and for oxygen, the same thing, constant specific heats. Okay. Well, let's approach it slowly. How could we find the answer to part A? How could we find those mole fractions of oxygen and nitrogen? Well, wouldn't the mole fraction of the oxygen be the number of moles of the oxygen divided by the number of moles of oxygen plus the number of moles of nitrogen? And I know that they're well mixed at the end, but the amount of oxygen isn't going up or down during the process. It's just shifting from A to B and mixing. And same with the amount of nitrogen. So what we need to do is we really can find the amount of the nitrogen initially, and it's confined only to tank A. And we're given the pressure, the temperature, and the volume. Can we calculate the amount of nitrogen in tank A initially? And that will be what? P tank A, or P1, let's put it like this, P1 V1 divided by R bar T1, all for the nitrogen initially confined to tank A. Does that make sense? How about the amount of oxygen that's initially in there? Well, the amount of nitrogen is 0.0980 kilomoles. How about the amount of oxygen? How about I pause and I want to see if you can calculate it. Show me the equation. It depends on the mass, and you divide by the molar mass. So this was 2 kilograms, and the molar mass of diatomic oxygen is 32.00 kilograms per kilomole. So I saw a lot of people 1/16. Perfect. The mole fraction of oxygen, 61.06%, and the mole fraction of the nitrogen turns out to be 38.94%. That's the answer for part A. What is the final mixture temperature in degrees C? How would you solve for the final mixture temperature? I'm gonna pause. I'm gonna walk around. We'll see what you got. All right. Write the first law for a closed system. The change in the total internal energy during a process is either going to be positive, going up because I brought in a lot of heat during that process from 1 to 2, or it's going to go down because I had some work out, 1 to 2, 1 to 2. Is that our first law? We draw for that large control volume, including the contents of both tanks. So we know it's well insulated, and we know it's rigid. No boundary work, and no heat transfer with the surroundings. So the change in the total internal energy is equal to 0. Hey, that's what we just worked on. This can be expressed as the number of moles of the oxygen, the molar specific heat, constant volume of the oxygen, T2 minus T1 of the oxygen. I mean, I'm getting tired of writing oxygen, 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 but you get the point. We also have the number of moles of the nitrogen, C sub V bar of the nitrogen, the final temperature minus the initial temperature of the nitrogen. So just this has to equal to 0, hence, there you go, the algebra. Somebody wants to write that on a mass basis? Sure, you can write it on a mass basis. You can write it on a mole basis or a mass basis. Is this temperature T2? The same as that temperature, T2. Yes. How do I move from this C sub V that's on a mass basis to a C sub V on a molar basis? C sub V bar is equal to C sub V, either multiply by cap M or divide by cap M. I can't remember. You help me out. I'll walk around and find out. All right, so the units will show that you multiply by cap M, and so you get C sub V bar just in the same way for C sub P bar if you want C sub P bar. So if they give you 1 on a mass basis, you can get it on a molar basis, likewise the other way. So these are calculatable. The number of moles we did calculate already. The initial temperature of the oxygen, we know that. It's 88 degrees C. The initial temperature of the nitrogen, we know that. It's 40 degrees C. This equation will work. And you should see the pattern. This type of equation where you have the final temperature of two things being mixed is the product of N C sub V of, let's say, the O2, the initial temperature of the O2, plus the amount, C sub V bar, left my bar off, of the nitrogen, the initial temperature of the nitrogen, divided by N C sub V of the O2, plus N C sub V of the N2. The equation just looks pretty. It looks symmetric. It looks good, right? Yes, come on. You should solve a number of these mixing so the final equilibrium temperature. The final temperature, 58.98 degrees C. I know that's too many digits, but there you go. So it's 59 degrees C. What about the final mixture pressure? How are you going to calculate the final mixture pressure? Use the ideal gas equation, because P2 times V2 is equal to N2, which is the amount of oxygen plus the amount of nitrogen, the total N of the mixture, R bar T2. We just calculated the final temperature. The volume, the final volume, well, we have to add up. V2 is the volume of tank A, which is given, plus the volume of tank B. Can I calculate the volume of tank B? Yes, you can. So you calculate the volume of tank B. Okay, the volume of tank B was 0.599 meters cubed. So the total volume is 0.899 meters cubed. That temperature, T2, you need it in Kelvin. So it's 332 Kelvin. And you calculate the final pressure. P2 is 493 kilopascal. And then check. Look, P2 better not be greater than or less than the initial pressures. One was high, 850. One was low, 313. It's somewhere in between. Just like the temperature, somewhere in between, right? Just a little check, sanity check. Last one, what about the amount of entropy produced? What's the roadmap to calculate entropy produced? I'm going to pause and let's see how many people get that right. A couple of you observed you do the second law analysis, right? For the second law for the process, you have that the final entropy minus initial entropy is how much is produced. You could put in a transfer term. I saw some people put in a transfer term in the equation with Q, but we know it's adiabatic with respect to the surroundings, so that Q is 0. So there's no entropy transfer. That's it. That's all. You just have to now evaluate, do the amount of the oxygen, and then you have the change in the molar, so it's going to be a C sub V, C sub P bar natural log final temperature over the initial temperature of the oxygen. All right. Minus R bar natural log the partial pressure of the oxygen in the final mixture. So that's going to be Y of O2 times P2 divided by P1 of the oxygen, and it was right here, 313 kilopascal. That makes sense? I need to scoot down a little bit. It was pure oxygen in one of the tanks. So that pressure, initial pressure of the oxygen, is just the pressure in tank B, which was 313 kilopascal. Then we add the amount of the nitrogen, C sub P bar, natural log of final temperature over the initial temperature of the nitrogen, minus R bar, natural log, the final pressure of the mixture times the mole fraction of the nitrogen in that mixture. That gives me the partial pressure of the nitrogen in the final state. And then I divide by the pressure 1 of the nitrogen, just like I divided by the pressure 1 of the oxygen. And the initial pressure of the nitrogen is 850 kilopascal, because it's pure nitrogen in tank A. So how do you get the C sub P bar? Well, just like we did over here, C sub P bar is equal to C sub P times the molar mass. Okay, you calculate then the entropy produced, the amount of entropy produced, 0.222 kilojoules per Kelvin